that we would like. Sorry. So the first talk is from Professor Mishra that we would like to thank for being here in this event. So his presentation is titled Class Groups of Real Cyclotomic Fields. So you have 13 minutes. The floor is yours.
Thank you very much. Let me try to share my screen.
Okay.
Are my slides visible?
Yes, yes.
Okay. So thank you, Professor, for your kind introduction. First of all, I would like to thank the organizers for their cordial invitation. Today, I will be talking about class groups of real cyclotomic fields. So the central problems in algebraic number theory is to understand the class groups of number fields. Number one, we try to look at what kind of groups occurs as a class group of a number field. And suppose if a group G occurs as a class group of some number field, then how often does it occur? Does it occurs as infinitely many times or only for finitely many number fields? So today in this talk, we'll be looking at the class groups of real cyclotomic fields. So let's start with Fermat-Last theorem. Fermat-Last theorem states that x to the power n plus y to the power n is equal to z to the power n does not have any non-trivial solution for n bigger than 2. The first method to tackle this problem was to factorize this left-hand side x to the power n plus y to the power n in the following manner. It can be written as a product of x plus y times x plus zeta n y times up to x plus zeta n to the power n minus 1 y, where this zeta n is the nth root of unity. And this factorization occurs in q zeta n, nth cyclotomic field. Basically, these are algebraic integers in the nth cyclotomic field. So suppose if the class number of q zeta n is 1, means its ring of integer has the unique factorization property. Then using some arguments, we can conclude that this particular Diophantine equation does not have any solution for exponent bigger than 2, non-trivial solution. So, but we know that there are only finitely many cyclotomic fields with class number equal to 1. What about other fields, means other cyclotomic fields? So Kumar found a way to deal with the failure of unique factorization domain, and he proved that if a prime P does not divide the class number of Pth cyclotomic field, means Q zeta P, for those exponent, he proved that this Diophantine equation, this Diophantine equation does not have any non-trivial solution. And such kind of primes are called as regular primes. And the primes which divides the class number of Q zeta P are known as irregular primes. It has been already proved that there are infinitely many irregular primes, and it is conjectured that there are infinitely many regular primes. So due to this evident connection between Fermat-Last theorem and the class groups of or class numbers of cyclotomic fields, mathematicians all around the world started to looking at the class groups of cyclotomic and real cyclotomic fields. So in this lecture, the class number of Q zeta n will be denoted by Hn, and the class number of its maximal real subfield Q zeta n plus zeta n inverse, which we also denote by Q zeta n plus, it will be denoted by Hn plus. Now we have a very beautiful theorem which says that we can factor Hn into Hn plus and Hn minus, where this Hn plus is the class number of real cyclotomic field, means maximal real cyclotomic field contained in Q zeta n, and this is known as the minus part of the class number of nth cyclotomic field. This Hn plus is in particular very easy to understand, and we can explicitly calculate this using Bernoulli numbers. On the other hand, this plus part, or the class number of maximal real subfield of Q zeta n, this is a bit complicated and quite mysterious, and to calculate it even for small values of n is very hard. So related to this quantity Hn plus, we have a famous Kumar-Vandiver conjecture, which says that P never divides the class number of Hp plus. This Hp plus is the class number of Q zeta P plus. Kumar himself verified this conjecture for prime up to 200. And later on Vandiver verified this conjecture for prime up to 600. And recently in 2017, Harry, Harvey, and Ong verified this conjecture for prime up to 2 to the power 31. But it was Miller who actually calculated this class number for prime up to 151. And he proved that class number of HP plus means class number of Q zeta P plus is exactly equal to 1 for prime up to 151. If you look at this result is quite stronger than this. This only says about the indivisibility of the class number of HP plus by prime P. But this exactly calculated means Miller exactly calculated the class number for primes up to 151. Weber also studied the class number of Q zeta 2n plus or 2nth real cyclotomic field, and he proved that the class number of Q zeta 2n plus is odd. Means 2 does not divide the class number of Q zeta 2n plus. And recently in 2011, Fukuda along with Komatsu proved that the class number of Q zeta 2n plus is not divisible by any prime up to 10 to the power 9. Related to the class number of this Q zeta 2n plus, we have a very well-known famous conjecture known as Weber's class number conjecture or problem, which says that the class number of Q zeta 2n plus is exactly equal to 1. Now, Weber himself verified this conjecture for n is equal to 1 and 2. Means Weber proved that this quantity H2 plus and H2 square plus is equal to 1. And in 1960, Cohen proved this conjecture for n is equal to 3. Later on, for n is equal to 4, it was verified by Bayer. And in 1982, van der Linden proved this conjecture equal to 5. And in the same paper, he proved this conjecture for n is equal to 6 under the assumption of generalized Riemann hypothesis. Again, recently, Miller proved this for n is equal to 6 without any condition. And in the next year, he proved this conjecture for n is equal to 7, again, under the assumption of generalized Riemann hypothesis. Okay. So related to the class number of this real cyclotomic field, we have another very well-known conjecture, Buhler-Pomerance-Robertson conjecture, which says that Q zeta P plus is containing Q zeta P square, it is containing Q zeta P cube, and so on. This conjecture says that after finite stage, the class number stabilizes. Means the class number at each stage is same. So this is what this conjecture says. Now there are two ways to understand the group. One way is to see what are the primes which divides its order and what are the primes which does not divide. And the other method is to look at its subgroup. Now let us try to understand the class groups of real cyclotomic fields using its subgroups. Cornell in 1979 proved that if we start with any finite abelian group G, it occurs as a subgroup of the class group of infinitely many cyclotomic fields. Now, the same question can be asked for real cyclotomic field or for totally real field. So, few years later, in 1984, Cornell along with Rosen proved that if we start with any finite elementary abelian P group, then it can be embedded in the class group of infinitely many real cyclotomic fields. And 3 years later, Osada proved the similar result for the groups of the form Z mod nz square. He showed that if we start with any group of the form Z mod nz square, then it can be embedded in the class groups of infinitely many real cyclotomic field. This was the last progress made in this direction. Then myself, along with Professor Scoof and Washington, proved that if we start with any finite abelian group G, we can embed it into the class group of infinitely many real cyclotomic fields. So we proved this in two ways. One is elementary and one is cohomological proof by Scoof, which I won't be talking about. I will be talking about elementary proofs. So let's start. Before proving this result, we will establish a relation between the real cyclotomic field and between the class group of real cyclotomic fields and the class group of its subfields. So first result is Suppose we start with the real quadratic field F and it is contained in some real cyclotomic field Q zeta n plus. Then the result says that the odd part of the class groups of this F is contained or is a subgroup of the class group of this Q zeta n plus. This is what this theorem says. As an immediate corollary, we can see that we know that Q root n is contained in Q zeta 4n plus for every n. So using this theorem, we can see that the odd part of the class group of this Q root n is a subgroup of the class group of this Q zeta 4n plus. Yes. So let's look at the proof of this theorem. First, look at the factorization of n, p1 to the power a1, p to the power a2, up to pr to the power ar. Now we know that this Q zeta n plus contains this Q zeta p1 to the power a1 plus Q zeta p to the power a2 plus, and so on. And this F is somewhere in between this Q zeta n plus and Q. Now, these KPIs, KP1 is somewhere here in such a way that the degree of this KP1 over Q is odd, and the degree of this Q zeta P1 to the power A1 plus over KP1 is purely even. By purely even, I mean it is just 2 to the power something. No other odd prime divide this upper degree. Similarly, we have KP2 somewhere here, KP3 and so on. Here we have KPR minus 1 and here we have KPR. So I have written it here. What are KPIs? So let H be the Hilbert class field of F and consider the compositum of F and KP1. Now we know that the degree of KP1 over K, this is odd, and F is real quadratic field, means the degree of F over Q is 2. Also, for each prime P, the real cyclotomic field, or in particular the cyclotomic field Q zeta P to the power A, is totally ramified at prime P. So any subgroup, any subfield of that field is also totally ramified. So we know that KP1 is totally ramified at prime P1. And since the degree of KP1 over Q is odd, therefore we can conclude that there does not exist any extension of F contained in the compositum of F and KP1 which is unramified. This immediately implies that the intersection of the Hilbert class field of F with the compositum of F and KP1 is F, which means this H, the compositum of H and KP1 is an unramified extension over the compositum of F and KP1. Also, the Galois group of this is isomorphic to the Galois group of H over F, and we know that this Galois group is nothing but the class group of F. So, and this is an unramified extension. So from here it follows that the class group of F is a subgroup of class group of the compositum of F and KP1. Now we repeat this process again and again up to KPR. So we get that the class group of F is a subgroup of the class group of this compositum F, KP1, KP2 and KPR. So now let's denote this compositum by L. This. And consider this map T from the class group of L to the class group of Hn plus. Remember, L is contained in Hn plus, and since we have already exhausted all the odd degrees here, so the degree of this Hn plus over L is purely even. Again, by purely even, I mean it is just 2 to the power something. And this map is nothing but, if you start with any ideal class, lift its representative to this Hn plus and take its ideal class. Now, we have a theorem for this map which says that if this degree is not divisible by a prime P, then this map is an injection on the P part. Now, as we know that this the degree of Hn plus over L is purely even, so this T map is an injection on odd part, means for all odd prime P. Now from here it follows that the odd part of the class group of L is a subgroup of the class group of this Hn plus. Now, this we know that the class group of L contains class group of F. Hence, The odd part of the class group of F is a subgroup of the class group of this Q zeta n plus. Actually, this theorem is a prototype of a much more general result, which we prove later. So the proposition is like this. Suppose we have the following setup. We have some number field F, which is contained in Q zeta n and which contains some cyclotomic field Q zeta m. And suppose this degree is not divisible by an odd prime Q. Then the result says that the Q part of the class group of F is a subgroup of the class group of this Q zeta n plus, or in terms of norm map, the norm map from the Q part of the ideal class group of Q zeta n is surjective to the Q part of the ideal class group of F. The result is similar. That was a prototype for this proposition, and that was the previous theorem is easier to understand. So I presented that result. The proof is same. We will be needing another lemma to prove our main result, which is as follows. That suppose we have two Galois extension K and L such that their intersection is just the field of rational numbers, and let M be the degree of K over Q and N be the degree of L over Q. Then the compositum of K and L, its class group contains a subgroup isomorphic to the class group of K to the power N, where this N is the degree of other field L over Q. Direct sum, class group of L to the power M. Here M is the degree of other field. This M is degree of K over Q. So we will be needing this lemma again and again. How? Let's see. So our main result was, if we start with a group G, finite abelian group G, we have to show that there exists infinitely many real cyclotomic field whose class group contains G as a subgroup. So let's start. We can write any finite abelian group like G2 direct sum G2 prime, where this G2 is a 2 group and this G2 prime has odd order. So first let's start with G2 prime. Yamamoto and Weinberger proved that given any positive number R, there are infinitely many real quadratic fields such that its class group contains an element of order R. And now using this previous lemma, okay, suppose the G2 prime is of the form, let's say, Z mod 3Z, direct sum Z mod 25Z. Now, by the result of Yamamoto and Weinberger, we know that there exists infinitely many real quadratic field whose class group contains Z mod 25Z as a subgroup. Moreover, there exists an element of the order 25, and also similarly for Z mod 3Z. Now, if we use this lemma, we have two real quadratic fields. Let's say K1 and K2. Their intersection is Q and their degree is 2. So their compositum of K1 and K2, their class group contains a subgroup isomorphic to the class group of K1 to the power 2, direct sum class group of K2 to the power 2. Now we know that the class group of K1 contains Z mod 25Z and exactly an element of order 25. So if we take its power 2, this is invariant. And similarly here, so Z mod 25Z direct sum Z mod 3Z occurs as a subgroup of the class group of K1 and K2. So now similarly, inductively, we can construct a compositum F of real quadratic fields such that the class group of F contains a subgroup isomorphic to G2 prime. Now, since we are taking a compositum of cyclic fields, so it will be an abelian number field. So by Kronecker-Weber theorem, it will be contained in some Q zeta n1. Moreover, since we are taking the compositum of real quadratic fields, it will be contained in the real or the maximal real subfield of this Q zeta n1. Now apply the previous proposition to this theorem. F is contained in Q zeta n1, and let's say some Q zeta m is contained here. Means Q zeta m is contained in F, F is contained in Q zeta n1. We know that the degree of F over Q is just 2 to the power something. So whatever Q zeta m is contained here, the degree of F over Q zeta m is just 2 power something. So no odd prime divides this degree. Hence, the odd part of the class group of F is a subgroup of the class group of this Q zeta n1. So, and we know that G2 prime is a subgroup of the class group of F, and G2 prime this has odd order. From here, it follows that Q zeta N1 contains this G2 prime as a subgroup. So this odd part has been handled. Now the even part is handled similarly using cyclic cubic fields. So for that, we use a result of Uchida, which says that given any positive integer R, there are infinitely many cyclic cubic fields with an element of order R in their class groups. Now, again, using the previous lemma, we take the compositum of such fields and we can construct a compositum F prime of cyclic cubic fields such that its class group contains G2 as a subgroup. Now, since this is a compositum of cyclic cubic field, again, this is abelian over Q. We again appeal to Kronecker-Weber theorem. It will be contained in some Q zeta N2. Now, again, we apply proposition here. The degree of F prime over Q is some 3 to the power something. So no, or in particular, 2 does not divide this degree. Hence, the even part of the class group of this F prime is a subgroup of the class group of this Q zeta N2. From here, we get that G2, this G2 is a subgroup of the class group of this Q zeta N2. Now we have two fields or two cyclotomic fields, Q zeta N1, Q zeta N2. Q zeta N2 contains G2 prime as a subgroup of its class group, and Q zeta N2 contains G2 as a subgroup of its class group. If we take the LCM of N1 and N2, let N be the LCM of N1 and N2, then we have Q zeta N, Q zeta N1 is here, Q zeta N2 is here. Now to this setup, we have Q zeta N, Q zeta N1. Apply this proposition. This, my F is nothing but Q zeta N1, M is N1, and this Q zeta N. So degree of Q zeta N1 over Q zeta N1 is nothing but 1. So its class group is a subgroup of this. Moreover, since we proved that the norm map is surjective, this norm map actually factors through the class group of this Q zeta N plus. From here, it follows that, from here it follows that the class group of this Q zeta N1 is actually a subgroup of the class group of Q zeta N plus. Similarly, the where is N2? Okay, I forgot to write. Similarly, if we look at this setup Q zeta N over Q zeta N2, the class group of this Q zeta N2 is a subgroup of the class group of Q zeta N. Means the norm map is surjective. But again, the norm map factors through Q zeta N plus maximal real subfield. So the class group of Q zeta N2 is a subgroup of the class group of Q zeta N plus. Now, G2 is also a subgroup of class group of Q zeta N plus and G2 prime also. So their direct sum is also a subgroup of its class group. Hence, we have constructed a real cyclotomic field whose class group contains G as a subgroup. And similarly, we can construct infinitely many cyclotomic fields. So this completes the proof of our main results. Thank you for your attention.
Thank you very much. Are there any questions? Any questions? No questions? So thank you again for being with us in this event. Thank you very much.
Thank you. I guess someone is raising his hand. I guess this is host.
Okay, Professor Shamsuddin. Yes.
Hello.
Hello.
I'm sorry, I wanted to connect by my phone so you can hear me. Thank you very much, Professor Mohit Mishra. I'm really so glad to attend your talk. This is very interesting. And I really like that you started your talk by recalling some of the most beautiful results concerning the cyclotomic field. And also, I'm really surprised that you could prove your very interesting theorem without any need to the unit groups. In fact, I'm used it, or at least the techniques that I'm used to use unit groups in each time I want to prove some results concerning the class group of number fields. So that was very interesting. And my question concerning are there any new developments concerning the unit groups of the cyclotomic fields, especially for the case where for the case of q zeta 2 to the power n, when n is greater than 5, I think. Yes, 5 or 6. Yeah.
Okay, right now I don't know any progress in that direction, so I can't comment.
Thank you very much. Okay.
Thank you.
Thank you, Professor Shamsuddin. Are there other questions?
Sorry, am I right that you didn't need to use unit groups when you proved your result? I didn't remark that you used the unit group, right?
No, we don't use unit group, but our this proof is only existential.
Yeah.
And Scoof proof is construction, means you can exactly find what kind of n you have to pick such that G occurs as a class group of those real cyclotomic fields. So the proof I presented, this is only existential proof. Scoof method gives you exact values of n such that G occurs as a subgroup of the class group of Q zeta n plus.
So nice. Thank you very much. Thank you very much.
Thank you, Professor. Other questions? Okay, so we thank you again for being here with us in this event. Thank you very much, Professor Mishra. So, Professor Nakatu, do you hear me?
Yes, Professor Rashida. Good afternoon.
Good afternoon. Hello. How are you?
I'm good.